Welcome to the Deep Dive, the show that's your shortcut to being well-informed. We strip away the jargon, try to give you the nuggets of knowledge you really need.
That's the goal.
So today, we're embarking on a journey. It's one that happens, well, thousands of times a day, every single time you click or send or stream something online.
Right. It's almost invisible, isn't it?
Totally invisible. It's this meticulously choreographed dance of data happening right beneath the surface of your everyday digital life. We're diving deep into the open systems interconnection, the OSI model. It's a really foundational concept in computer networking.
It is, and it explains, in surprisingly intricate detail, how your digital information actually moves across networks. From your device to wherever it's going, and then back again.
Exactly.
And it really is a conceptual marvel. It's not a protocol suite itself like TCP/IP, but the OSI model provides this kind of universal roadmap. Think of it as a lingua franca for network engineers, for IT professionals.
A common language.
Yeah. A common language to understand, and crucially, to troubleshoot and secure our incredibly complex digital world.
So for this deep dive, we've gathered, well, quite a stack of sources.
We have everything from detailed technical write-ups, academic analyses looking at its history and its modern relevance.
And also some really fascinating real-world stuff, right? Like troubleshooting discussion.
Exactly.
Yeah.
From seasoned IT pros, sharing their war stories on platforms like Reddit. Really practical insights there.
Okay. So our mission today is basically to demystify this powerful framework, give you a clear, concise understanding of the how behind, well, everything you do online.
And hopefully you won't just grasp the theory, but you'll really appreciate its profound practical implications too.
Okay, let's unpack this. It is quite an intricate process. So to really get a handle on what's happening, let's maybe start with a simple scenario, something relatable.
Good idea.
Okay, imagine Sarah. She wants to send a photo, maybe of her dog, to her friend Max.
Classic example.
Right. She opens her chat app, finds the photo, hits send. Now, what actually unfolds after that single tap?
Because it feels instantaneous.
It feels like magic, but it's far from a single instantaneous leap across the internet. Instead, it's this meticulously choreographed dance through 7 distinct layers.
7 layers.
Each one adding crucial information, transforming the data. It's a term. Encapsulation.
Encapsulation, exactly.
Yeah.
Wrapping it up layer by layer. This whole journey begins right there on Sarah's phone, moving downwards through each of these layers, getting that photo ready for its grand voyage across the network.
Okay.
And a core insight here really is that every piece of data follows this path. Doesn't matter if it's Sarah's dog photo, a video call you're on, a bank transaction, or even just a simple text.
It all goes through the same steps.
It all follows this layered path, this structured approach, the OSI model. It gives us this consistent, universal language for how all these different systems communicate. Our sources consistently stress that it's a conceptual framework. It's designed specifically to allow, different hardware and software, maybe from totally different companies, to interoperate, to talk to each other seamlessly.
So it doesn't matter if Sarah has an iPhone and Max has an Android.
Exactly. Or what brand of router is in the middle. They can all speak and understand the same data language thanks to these universally understood layers.
Okay, layer 7, application layer. This is where you, the user, you first interact with the network, right? Even if you don't realize it.
Precisely. When Sarah taps send in her chat app, the application layer is where her intention sharing that photo gets translated into a specific network request.
Now, you said it's not the app itself. That's an important distinction.
It is. It's not the chat app's code directly, but rather the protocols the application uses to talk to the network. It's about the services the app requests.
Okay, so how does this layer translate what we want to do into something the network understands?
Well, fundamentally, it's about identifying the communication partners, like finding Max's chat app on his phone.
Right.
And checking resource availability. Does Max's phone even have the app running? Does the network path seem available? It also handles things like authentication sometimes, ensuring communication interfaces exist.
So it's the starting point for generating an email, making a video call.
Exactly. All those user-facing tasks originate here. And at this initial stage, interestingly, no extra headers or trailers are added to the data itself, the protocol data unit, or PDU.
PDU.
Yeah, that's just the term for the chunk of data at each layer. Here at layer 7, the PDU is simply data, the raw stuff Sarah wants to send.
Okay, and protocols here are things we might recognize.
Oh, absolutely. Think HTTP and HTTPS for web browsing. SNTP, IMP, POP3 for your email, FTP for file transfers, even DNS, the system that turns website names into IP addresses.
Wow. Okay, DNS is layer 7.
Yep. And things like WhatsApp Web or a Zoom call, they all start their network journey right here. It's basically the what you want to do with the network layer.
Okay, so layer 7 figures out what to send and where. Now, moving down to layer 6, the presentation layer, what's its job?
Well, once the app decides what data to send, Layer 6 steps in with a really vital role: translation and formatting.
Translation, like languages.
Sort of.
Yeah.
Imagine sending a message or that dog photo to someone whose device stores information in a completely different format or uses a different character set.
Ah, okay, so compatibility.
Exactly. This layer acts as the universal translator and formatter. It makes sure Max's phone can actually understand and correctly display that dog photo, regardless of how Sarah's phone might natively represent data. That's why it's often called the syntax layer.
Makes sense. So how does it manage this translation and formatting? What does it actually do?
If we connect this to the bigger picture, like the early days of networking, this layer was absolutely critical. You had mainframes talking to PCs, totally different systems.
Right, completely different worlds.
Yeah. So its primary functions include data translation, maybe converting between character codes like ASCII and EBC, DIC, ensuring text is readable everywhere.
Okay, what else?
And perhaps more visibly today, it handles data compression, making data smaller so it sends faster. Think JPEG for images, MPEG for video, or even just ZIP file compression.
So Sarah's dog photo probably gets compressed here.
Very likely, yeah. Into a JPEG, most probably. And crucially, Layer 6 also manages encryption and decryption. This is fundamental for security.
Ah, like HTTPS.
Precisely. SSL and its successor TLS, they operate here conceptually. They secure your web browsing. So when Sarah sends her photo, Layer 6 might compress it and encrypt it for privacy.
So even though some functions might be handled elsewhere now.
Right. Some functions, especially translation, might be handled by the application itself today. But encryption is a key example of Layer 6's enduring role. It's still conceptually vital for secure communications.
And the PDU here, still just data.
Still called data, yep. But now it's formatted, maybe compressed, maybe encrypted, ready for the next step.
All right, layer 7 decided what to send. Layer 6 formatted and maybe encrypted it. Now, layer 5, the session layer. This sounds like it manages the conversation itself.
That's a great way to put it. Now that the data is ready, we need to make sure the communication link or session stays open, organized, and properly managed from start to finish.
Like a moderator.
Exactly like a moderator. It establishes, manages, and ultimately terminates the communication session between Sarah's device and Max's device. It ensures there are no interruptions, that both sides know whose turn it is to talk, maintaining a continuous, synchronized flow.
Okay, now I've heard this layer, along with layer 6 sometimes, is seen as a bit, well, empty in modern networks, like in the TCP/IP model.
That's an excellent observation, and it really highlights a philosophical difference. The OSI model aimed for theoretical completeness, very distinct layers. TCP/IP was more pragmatic.
Right? Built for what works.
Pretty much. So the key insight is that strict layering, especially with these higher conceptual layers, can sometimes add overhead. Many of the session layer's functions have been absorbed often into the application layer or maybe the transport layer for efficiency in today's TCP/IP world.
But conceptually, what was its role? What did it do?
Conceptually, its purpose is vital: managing the dialogue. For instance, determining if communication is full duplex, both sides talking and listening at once, like a phone call.
Right.
Or half duplex, where only one side can send at a time, like a walkie-talkie.
Right.
It's also responsible for things like user logons and logoffs. And for really large data transfers, it provides synchronization and checkpointing.
And checkpointing, what's that?
Imagine downloading a huge file, and the connection drops halfway through. Checkpointing allows the transfer to potentially resume from the last checkpoint instead of starting all over again. Saves a lot of time and frustration.
Ah, that's useful.
Very useful. Protocols like RPC, Remote Procedure Call, which lets programs run code on other machines across the network, or NetBIOS for local network stuff, or even some older VPN protocols like PPTP traditionally operate here.
So logging into a website or joining a Zoom meeting, that involves session management.
Fundamentally, yes. Those actions rely on session management principles, even if the specific code handling it now often lives in Layer 7 or Layer 4. The PDU here. Still data, but it's now within the context of an established managed session.
Okay, now we're getting down to layer 4, the transport layer. This feels really important. You described it as the heart of reliability
Yeah.
or speed.
It really is pivotal for the actual end-to-end communication. This is arguably where the core of reliable data transfer truly begins. It's all about getting your data from Sarah's application all the way to Max's application reliably and efficiently.
So if Sarah's dog photo, after layer 6, maybe compressed it, is still a big chunk of data.
Right. Layer 4 takes that chunk and breaks it down into smaller, more manageable boxes. We call these segments if it's using TCP for reliability or datagrams if it's using UDP for speed.
Segments or datagrams. Okay, so it acts as the backbone for that end-to-end delivery.
Absolutely. Making sure the entire message gets from Sarah's app to Max's app, it manages crucial functions like flow control.
Flow control, like not sending too fast.
Exactly. Preventing a fast sender, maybe Sarah's phone on Wi-Fi, from overwhelming a slow receiver, maybe Max's phone on a weak cell signal. It uses mechanisms like a sliding window where the receiver basically tells the sender, okay, I'm ready for this much data now, preventing floods.
And what else?
It also handles error handling, using things like checksums to detect corrupted data and retransmission timers. If a segment gets lost or damaged, Layer 4 can notice and ask the sender to send it again.
Okay, that's the reliability part.
That's TCP's reliability, yes.
Yeah.
It also performs segmentation, the breaking down part, and multiplexing.
Multiplexing.
That allows multiple applications on your device, your browser, your email, your chat app, to share the same single network connection simultaneously. Without multiplexing, you'd only be able to do one thing online at a time.
Ah, okay. And how does it know which data goes to which app on Max's phone?
Great question. It uses port numbers. Think of them like apartment numbers on a building's street address, the IP address. Port numbers provide service point addressing. For example, standard web traffic usually goes to port 80 or 443. Email often uses port 25, 143, or 993. This ensures the data reaches the correct application.
Got it. And you mentioned two main ways it works, TCP and UDP.
Exactly. The two heavyweights here are TCP, Transmission Control Protocol, and UDP, User Datagram Protocol.
What's the difference again?
TCP provides reliable, connection-oriented delivery. It sets up a connection first, numbers the segments, checks for errors, acknowledges received segments, and retransmits lost ones. It's meticulous.
So that's for things where you need every bit, like downloading a file.
Precisely. File downloads, email, secure web browsing, HTTPS. They all rely on TCP because data integrity is paramount.
And UDP.
UDP is the speed demon. It offers a faster, connectionless, and unreliable service. It doesn't establish a connection, doesn't number datagrams, doesn't wait for acknowledgments, it just sends.
Why would you want unreliable?
Because sometimes speed is more important than perfect delivery. Think real-time applications, online gaming, voice calls like WhatsApp, video streaming. If a tiny piece of a video frame gets lost, it's better to just skip it and keep the stream flowing smoothly than to pause everything waiting for a retransmission. A slightly lost packet is better than a delayed one that causes stuttering or lag.
Okay, that makes sense. Different tools for different jobs.
Exactly. This flexibility is key to how the internet works for so many different kinds of applications. And at this layer, the PDU is now officially a segment for TCP or a datagram for UDP with the necessary layer 4 header added.
All right, layer 4 broke our data into segments or datagrams. Now, layer 3, the network layer, you called this the GPS of the internet. Sounds like it handles the big picture routing.
That's the perfect analogy. Those smaller boxes from layer 4 now become packets. And layer 3's job is to figure out the best route for these packets across the entire global internet.
Not just on my local network, but getting it across different networks.
Exactly. It's not just about getting data from your laptop to your home router. It's about getting it from your network, potentially through dozens of other networks, to the final destination network, maybe on the other side of the world. It ensures each packet navigates this vast global web from Sarah's phone's network to Max's phone's network.
How does it manage that? What's the key information it uses?
The key is logical addressing. Layer 3 adds crucial IP, Internet Protocol, headers to the segments or datagrams, turning them into packets. These headers contain the source and destination IP addresses.
Like the public IP addresses we get from our internet provider.
Precisely. Either IPv4 addresses, the older standard, or the newer IPv6 addresses. These IP addresses are like the unique street addresses for devices on the global internet.
And what uses these IP addresses?
Routers. Routers are the primary devices operating at layer 3. They sit at the junctions between different networks. When a packet arrives at a router, the router examines the destination IP address in the header.
And then what?
It consults its internal routing table, essentially a map of the internet it knows about, to determine the most efficient path, the best next hop or next router, to send the packet towards its final destination network. This might involve many, many hops across the internet.
So routers are constantly making decisions about the best path.
Constantly, using various routing protocols like OSPF or BGP to learn about network paths and make intelligent forwarding decisions. We also see ICMP here, which is used for diagnostics, like the ping command, to test reachability or traceroute to see the path packets take.
So for Sarah's photo, Layer 3 puts her IP and Max's IP on the packets, and routers use Max's IP to guide them across the globe.
That's the core idea. It enables this inter-network communication, allowing devices anywhere in the world to talk to each other. The IP address provides that globally unique, logical destination, telling us where the packet needs to go in the big picture, abstracting away all the physical wires and local networks in between.
And the PDU is now a packet.
Correct. The PDU at Layer 3 is a packet, complete with its network layer header containing those crucial IP addresses.
Okay, Layer 3, the network layer, figured out the global path using IP addresses. But you mentioned packets taking hops between routers. How does a packet get from, say, my computer to my router, or from one router to the very next one in the chain?
Now we're zooming back into the local picture. That's the job of Layer 2, the data link layer. The network layer found the overall route, but now the data needs to get across the local block, from one device to the next directly connected device on the same network segment.
So it's like a local delivery service for each step of the journey.
Perfect analogy. Layer 2 takes those packets from Layer 3 and wraps them again, this time into frames. And it adds local physical addresses and checks for errors, specifically within that immediate network segment, that single hop.
Wrapping them again, so headers and trailers.
Often, yes. Layer 2 adds a header containing physical addresses and often a trailer containing an error check code. Its main goal is ensuring reliable data transfer between directly connected devices on the same link.
Physical addresses, you mean MAC addresses.
Exactly. MC Media Access Control Addresses. These are unique hardware identifiers baked into every network interface card, NIC, whether it's Ethernet or Wi-Fi. Layer 2 uses the MC address of the next device on the local network path as the destination for the frame.
So IP addresses get you across the internet, and MAC addresses get you to the next machine on your local network.
You've got it. That's the crucial distinction. IP for the end-to-end journey, MAC for the immediate next hop.
And how does Layer 2 ensure reliable local transfer?
It has mechanisms for error detection, most commonly the CRC, cyclic redundancy check, which is usually in the trailer. This helps detect if the frame got corrupted during transmission across that specific wire or wireless link. Imagine a noisy connection. Layer 2 tries to catch those errors before the packet gets passed up to Layer 3 on the receiving end.
Making the physical connection seem error-free.
Ideally, yes. It makes the physical layer appear much more reliable to the network layer above it. This layer is often conceptually divided into two sublayers: LLC, logical link control for error flow control, and MMAC, media access control, for managing access to the physical medium, like deciding whose turn it is to talk on a shared Wi-Fi channel.
And what technologies live here?
Ethernet is the classic wired example. Wi-Fi, IEEO 2.11, is the big wireless one. When your laptop talks to your router via Wi-Fi or when devices connect to a network switch, that's all happening at Layer 2.
Okay, and the PDU is a frame now.
Correct. The PDU at Layer 2 is a frame wrapped around the Layer 3 packet with its own Layer 2 header and trailer.
We've finally reached the bottom. Layer 1, the physical layer. After all that meticulous preparation, formatting, encrypting, segmenting, packetizing, framing, we get to the actual physical act of sending.
We do. This is where the rubber meets the road, or perhaps more accurately, where the electrons meet the copper or the light meets the fiber.
So it strips everything down to the bare essentials.
Absolutely. Layer 1 takes those frames from Layer 2 and converts them into their most basic form. A raw stream of bits, just ones and zeros. And then it pushes those bits out onto the physical medium, the wires, the fiber optic cables, the radio waves.
The literal wires and waves layer.
And that's it. It's the absolute foundation. All the other layers rely on Layer 1 successfully transmitting and receiving these raw bits.
What exactly does it coordinate to turn abstract bits into, actual signals?
It's quite a bit. Layer 1 defines all the mechanical and electrical specifications. Things like the type of cabling, Cat6 Ethernet, single-mode fiber, coaxial cable, the connectors RJ45, LC connectors for fiber. The precise voltage levels used to represent a 1 or a 0 on a copper wire. The bit rate, how fast are we sending those bits? Megabits, gigabits per second.
Okay.
It also handles synchronization, making sure the sending and receiving clocks are aligned so the receiver knows when one bit ends and the next begins. And modulation, how digital data bits gets converted into analog signals suitable for transmission over the medium, like changing radio wave properties for Wi-Fi.
So network interface cards, NICs, operate here.
Yes, the physical part of the NIC operates here. Also, older devices like hubs and repeaters, which just regenerate and blast out signals. Any problem like a broken wire, interference from a microwave oven affecting Wi-Fi, signal loss because a cable is too long. That's a classic layer 1 issue,
Right.
impacting everything above it.
Directly.
Yeah.
And it's fascinating because even here, there's complexity. You mentioned a layer 0.
Yeah, it's an interesting concept you sometimes hear in high-end networking, especially with fiber optics. Technologies like CWDM and DWDM allow multiple different wavelengths of light, each carrying a separate data channel, to travel over a single strand of fiber.
Wow.
Layer 0 refers to that underlying infrastructure, the physics of transporting those light waves themselves. It just reminds us that even the physical layer has deeper layers of complexity, especially as we push for faster and faster speeds.
So at layer 1, the PDU is simply...
Bits. Raw ones an hour is being sent as signals.
Okay, so Sarah's dog photo, meticulously packaged layer by layer, transformed into a stream of bits at layer 1, is now actually being sent out from her phone.
The journey begins.
But, like we said, it doesn't just magically float directly to Max's phone. It has to navigate the network.
The vast, intricate web of networks.
Right. And that's where these intermediate devices come in. They act as crucial checkpoints and navigators along the path.
And this is where understanding the OSI model becomes really practical, because each type of intermediate device operates primarily at a specific layer.
Understanding which device does what at which layer helps visualize the path.
Exactly. It helps us conceptualize how data actually gets from point A to point B, especially when it has to cross multiple networks, making several hops between devices. Each device has a specific job defined by the OSI layer it works at.
Let's start at the bottom again. Layer 1 devices, you mentioned hubs and repeaters earlier. These are pretty basic, right?
Very basic. They operate purely at the physical layer, layer 1. They really just deal with the raw electrical or optical signals.
Hubs, you call them dumb devices.
Pretty much, yeah. A hub receives a signal on one port, regenerates it to boost its strength, and then simply broadcasts that identical signal out to all other connected ports.
Sends it everywhere, regardless of destination.
Everywhere. It has absolutely no knowledge of MSC addresses or IP addresses. It just repeats everything to everyone on that network segment.
Sounds inefficient. And maybe insecure.
Highly inefficient, yes. It leads to a lot of unnecessary traffic and collisions where multiple devices try to talk at once. And yeah, insecure because anyone connected to the hub could potentially see traffic not meant for them. Hubs are largely obsolete in modern networks for these reasons.
And repeaters. Similar idea.
Similar, but even simpler in a way. A repeater typically just has 2 ports, and its sole job is to regenerate a signal between 2 cable segments to extend the distance the signal can travel. Purely a layer 1 signal booster.
Okay, moving up to layer 2, the data link layer. We have switches. These sound much smarter than hubs. You call them intelligent traffic cops.
That's a good description. Switches are a massive leap forward from hubs. They operate at layer 2, and they do understand MC addresses.
How does that help?
Switches learn which devices are connected to which of their ports. They do this by inspecting the source MC address of incoming frames. They build a little table called a MI address table or CAM table, mapping MI addresses to port numbers.
Okay, so they know who lives where on the local network.
Exactly. Then, when a frame comes in destined for a specific MC address, the switch looks up that destination MAC in its table.
And sends it only to the right port.
Precisely. Instead of broadcasting it everywhere like a hub, the switch forwards the frame only out the specific port connected to the destination device.
They must cut down on traffic immensely.
Hugely. It dramatically reduces unnecessary traffic and collisions on the local network segment, significantly boosting performance. Switches allow multiple conversations to happen simultaneously between different pairs of devices connected to the switch without interfering with each other. They are fundamental to modern local area networks, LANs.
And then, the big guns. Layer 3, the network layer. We have routers, the global navigators. Their job is connecting different networks together, right? Getting Sarah's photo across the internet.
That's their primary role. Routers operate at layer 3, and they connect disparate networks. They use logical IP addresses, not physical MSC addresses, to make routing decisions.
So walk us through what happens when data arrives at a router. Let's say a frame carrying a packet for Max arrives from Sarah's local network switch.
Okay, so the layer 2 frame arrives at the router's network interface. The first thing the router does is decapsulation.
Unwrapping it.
Exactly. It strips off the layer 2 header and trailer, the Ethernet frame stuff, for example, exposing the layer 3 packet contained inside.
Now it can see the IP addresses.
Right. It examines the destination IP address within that packet's header. Then it consults its internal routing table. This table contains information about which network paths lead towards various destination IP networks.
And it figures out the best way to send it forward.
It determines the best next hop, usually the IP address of the next router in the path, to get the packet closer to its final destination network. Now remember, a device operating at layer N also needs all the layers below it.
So a layer 3 router needs layer 2 and 1.
Absolutely. It needs layer 1 to physically receive the signal and layer 2 to understand the incoming frame before it can even get to the layer 3 packet.
Okay, so it knows the IP address of the next router. But to send it over the local link to that next router, it needs its MPay address, right?
Excellent point, yes. If the next hop is on the same local network segment as the router's outgoing interface, the router needs the MPay address of that next hop device. This is where ARP, Address Resolution Protocol, comes in.
How does ARP work?
If the router knows the next hop IP, say 10.0.1, but not its MAC address, it sends out an ARP request on that local network segment, basically shouting, "Who has IP address 10.0.0.1? Tell me your MAC address."
And the device with that IP replies.
The device with 10.0.0.1 replies directly to the router with its MAC address. Now the router knows the layer 2 address it needs.
So then it sends the packet.
Almost. Now it performs re-encapsulation. It takes the original layer 3 packet, with Sarah's and Max's IP addresses still intact, and wraps it in a brand new layer 2 frame. But this new frame's destination MMAC address is the MS address of the next hop router it just discovered via ARP.
Ah. So the IP addresses stay the same for the whole journey, but the M addresses change at every single hop.
You've nailed it. That's the fundamental principle of routing across networks. Decapsulate, check IP, find next hop IP, find next hop IMARI, using ARP if needed, re-encapsulate with new MS, send.
And this happens over and over.
Potentially hundreds of times for a single packet crossing the internet. It's this constant stripping and rewrapping that allows data to navigate the global maze. It's a beautiful illustration of how these layers cooperate, abstracting away immense complexity. So eventually, Sarah's dog photo just appears on Max's screen.
Okay, Sarah's dog photo, after that incredible journey hopping across routers, changing frames at every step, has finally arrived. The signals reach Max's phone.
Mission accomplished, almost.
Right, because it's still not a viewable image yet.
Yeah.
It's arrived as, what, electrical signals?
Yeah.
Radio waves.
Yep. And then bits, then frames, then packets, then segments, all still wrapped up in those layers of headers and trailers added on Sarah's end.
So now it has to go back up the stack on Max's phone, reversing the whole process.
Exactly. This upward journey is called decapsulation. Layer by layer, Max's phone needs to meticulously peel off the packaging that Sarah's phone added until the original photo data is revealed. It's just as critical and complex as the downward encapsulation.
Like opening a series of nested envelopes.
Perfect analogy. Each layer only opens its corresponding envelope, checks the contents for its specific purpose, like checking the address or looking for errors, and then passes the inner envelope up to the next layer. It's a staged, logical process.
So the ascent starts right at the bottom again. Layer 1, the physical layer on Max's phone. What happens first?
Okay, Max's phone's physical hardware, maybe its Wi-Fi chip, receives those incoming signals, radio waves in this case. Layer 1 converts these raw signals back into a digital stream of bits, ones and zeros.
Just raw bits.
Raw bits. Then, Layer 1 hardware assembles these bits into a coherent data link layer frame and passes that complete frame up to Layer 2. Any corruption caught at the signal level would be handled here or noted.
All right, frame arrives at Layer 2. What checks happen now?
At Layer 2, the data link layer, Max's phone's NIC takes the frame. First, it checks the destination MIC address in the Layer 2 header. Does it match the phone's own MIC address?
Assuming yes.
Assuming yes, it then performs an integrity check, usually by calculating the CRC from the frame's data and comparing it to the CRC value stored in the frame's trailer.
To see if it got garbled during that last hop.
Exactly. If the CRC check passes and the MSC address is correct, Layer 2 considers the frame valid. It then strips off the Layer 2 header and trailer, exposing the network layer packet that was hidden inside.
Unwrapped one layer.
Unwrapped one layer. That clean packet is then passed up to Layer 3.
Okay, Layer 3 receives the packet, another address check.
Absolutely. At layer 3, the network layer, Max's phone checks the destination IP address in the packet's header. This confirms that the packet has reached its ultimate logical destination across the internet.
Does it match Max's phone's IP address?
If it matches, great. The phone knows this packet is definitely for it. Layer 3 then removes its own header, the IP header, leaving behind the transport layer segment, or datagram, that was inside.
Got it. So each layer peels off its envelope, does its checks, and passes the contents up.
Precisely. It's a peer-to-peer process. Sarah's layer 3 talks to Max's layer 3 via the IP header. Sarah's layer 2 talks to the intermediate router's layer 2 via the frame header, and so on. Each layer deals only with its own control information.
Okay, the low-level addresses and frame stuff are gone. We're left with segments, the chunks created by layer 4 on Sarah's side. Now Max's phone needs to put the photo back together.
Right. The journey continues up to layer 4, the transport layer, and this is where the critical reassembly happens, assuming TCP was used.
How does it reassemble? The segments might have arrived out of order, right?
Yep. They very well might have, thanks to different paths packets can take. But TCP added sequence numbers to each segment back on Sarah's phone. So Max's layer 4 uses these sequence numbers to painstakingly put all the individual segments back into their original correct order.
Like assembling a jigsaw puzzle using the numbers on the back.
That's a great way to think about it. It ensures there are no gaps and no jumbled parts. Layer 4 also performs final error checks on the reassembled data stream.
And does it tell Sarah's phone everything arrived okay?
If it's TCP, yes. It sends acknowledgement messages back to Sarah's phone, confirming which segments were received successfully. This is key to TCP's guaranteed delivery. Once all segments are received and reassembled correctly, the complete original data stream, the dog photo content, is passed up.
Okay, photo reassembled. What are the final steps before Max actually sees it?
Almost there. The data goes up to layer 5, the session layer. Conceptually, this layer manages the end of the communication session, releasing any network resources that were held open during the transfer.
Tidying up.
Tidying up, exactly. Then it moves to layer 6, the presentation layer. If Sarah's phone compressed the photo, like JPEG compression, layer 6 now decompresses it. If it was encrypted, layer 6 decrypts it using the necessary keys. It translates the data back into a format the final application can understand.
Preparing it for display.
Preparing it for display. And finally, at layer 7, the application layer, that fully reassembled, decrypted, decompressed, correctly formatted data, Sarah's pristine dog photo, is passed directly to Max's chat application.
And then it appears on his screen.
And then it pops up. So from the user's perspective, it feels instantaneous, taps and photo appears. But underneath, that whole complex symphony of encapsulation, routing, decapsulation, reassembly, it all happened in fractions of a second.
That's the beauty of layered abstraction, hiding all that complexity.
Yeah, it really is. Delivering the information seamlessly while masking the immense work happening underneath.
Okay, we've gone deep into these 7 layers. It's elegant, it's logical.
Yeah.
But you mentioned earlier, the internet we actually use runs on a different model, TCP/IP.
That's right. It's one of the fascinating historical twists in networking.
So if OSI is so well structured, why didn't it become the standard? Why did TCP/IP win the protocol wars, as some call it?
Yeah, the protocol wars. It's a great story and a real lesson in technology adoption. It really boils down to practicality, timing, and existing momentum.
Okay. So OSI was developed by?
Developed by the ISO, the International Standards Organization, formally published around 1984. It was designed from the ground up to be the comprehensive protocol-independent framework. 7 distinct layers, beautiful separation of concerns, aiming for universal communication. An academic ideal, really.
And TCP/IP.
TCP/IP emerged earlier from DARPA, the U.S. Department of Defense's research agency, powering the ARPANET. It was more practical, protocol-driven, built by engineers who needed something that worked. It has a simpler, streamlined 4-layer architecture.
4 layers. How do they map to OSI 7?
Roughly like this. OSI's top 3 layers, Application 7, Presentation 6, and Session 5, all get collapsed into TCP/IP's single application layer.
Ah, that explains why 5 and 6 sometimes feel empty in practice.
Exactly. Their functions were often just built into the applications themselves or handled within TCP/IP's broader application layer. Then OSI's layer 4, transport, maps pretty directly to TCP/IP's transport layer. That's where TCP and UDP live in both models.
Okay.
OSI's layer 3 network maps to TCP/IP's internet layer, which is dominated by the IP protocol. And OSI's bottom 2 layers, data link 2 and physical 1, map to TCP/IP's network access layer, sometimes called link layer.
So simpler structure. Why did that win out? You mentioned timing.
Timing was huge. By the time the OSI standards were finalized and published in '84, TCP/IP was already widely deployed and working effectively on the ARPANET since 1983. The internet wasn't going to wait for a theoretically perfect model. It needed a working model, and TCP/IP was it.
Inertia is powerful.
Incredibly powerful. Plus, implementation. OSI's rigorous 7-layer design, especially with those distinct session and presentation layers, turned out to be complex and, frankly, difficult to implement efficiently back then. Early OSI software was often buggy and slow.
Giving it a bad reputation.
It did. TCP/IP, being simpler and more, let's say, organically grown, was easier to get working. It was built by practitioners focused on results, not necessarily academic purity.
Any other factors? Politics? Sociology?
Definitely. TCP/IP became closely associated with Unix, which was exploding in popularity in universities and research labs, the very places ARPANET was growing. And crucially, TCP/IP had killer apps from the start.
Killer apps?
Yeah, functional applications that people immediately found useful. Things like Telnet for remote login, FTP for file transfer, and SMTP for email. These ran on TCP/IP and provided real value, driving adoption like crazy. People started using TCP/IP because it did useful things right away.
It's that worse is better principle. A simpler working solution beats a complex, perfect one that arrives too late.
A classic example of it. So TCP/IP became the de facto standard for the internet. But, and this is important, despite TCP/IP winning the protocol war, the OSI model won the intellectual battle. Its clarity and structured approach made it the definitive lingua franca for teaching, understanding, and troubleshooting networks. It's still the framework everyone learns.
Okay, so even though we run on TCP/IP, the OSI model is still incredibly relevant, especially for troubleshooting. How does it help when, the internet breaks?
Yeah.
Which it does. All the time.
All the time. And this is where the OSI model truly shines in everyday IT life. It gives you a structured, logical way to figure out where the problem is. Instead of just randomly guessing, you can systematically work through the layers.
Turning the internet's down into a step-by-step diagnosis.
Exactly. It transforms that vague frustration into precise, logical steps. There are generally 3 main approaches people use based on the model.
Okay, what are they?
First is bottom-up. You start at layer 1, the physical layer. Ask the basic questions. Is the cable plugged in? Is the Wi-Fi on? Are the lights blinking on the device?
The simple stuff first.
The simple stuff first, because, honestly, a surprising number of problems are layer 1 issues. If layer 1 looks good, you move up to layer 2. Is the switch port working? Is the MAC address learned? Then layer 3, do I have an IP address? Can I ping my gateway? And so on.
Makes sense. What's the second approach?
Top down. You start at layer 7, the application layer. Can I browse any website or just this one? Is the problem only happening in my email client? Or are other apps affected too? If the application layer seems fine, you move down. Maybe check layer 4 is a firewall blocking the port.
When would you use top-down?
It's often useful if you suspect the issue is specific to a particular application or service rather than a general connectivity problem.
Okay, and the third?
Divide and conquer. This is often the most efficient. You start somewhere in the middle, usually layer 3. A great tool here is the ping command.
Ah, good old ping.
Good old ping. You try to ping a known reliable IP address, maybe your router's gateway or a public DNS server like 8.8.8.8.
What does the result tell you?
If the ping succeeds, it generally means layers 1, 2, and 3 are working okay between you and that target. The problem is likely higher up in layer 4 or above, maybe a firewall, maybe the application itself.
And if the ping fails?
If the ping fails, the problem is likely at layer 3 or below. You don't need to worry about firewalls or applications yet. Focus on IP addressing, routing, cables, switches, etc. It helps you rapidly narrow down the scope.
That's really practical. Can you give some real-world examples for each layer? Maybe like those Reddit stories?
Oh yeah, IT forums are full of these. Layer 1. Classic examples are broken Ethernet cables, a faulty physical port on a switch, or simply an unplugged cable. That sysadmin who spent 3 days finding a switch that was just slightly loose. Pure layer 1 agony. Layer 2. Things like a bad switch, maybe misconfigured, 2 devices accidentally having the same ACK address, a AM conflict, or a computer being plugged into a switch port configured for the wrong VLAN, isolating it from the network it needs to be on. Layer 3. A router having a bad route in its table, sending packets the wrong way. A device having the wrong IP address or subnet mask. Or, again, an interface being on the wrong VLAN, which affects its IP connectivity. Layer 4. A firewall blocking a specific TCP or UDP port needed by an application. weird TCP performance issues due to windowing problems, a download failing and needing a restart because TCP couldn't guarantee delivery. Layer 5, a VPN failing to connect because the session negotiation fails. Authentication issues like mismatched pre-shared keys, PSKs. Getting mysteriously logged out of your online banking site after your connection flickers, that's a session interruption. Layer 6, problems with SSL/TLS certificates on websites, like expired certificates causing browser warnings. Issues where data gets corrupted because of incompatible compression or encoding between systems. Even weird formatting issues when sharing files. Layer 7. This is often application-specific bugs. Maybe a website requires HTTP3, but your browser doesn't support it. Problems with SSH configurations preventing login. And the big one, DNS errors, where you can't resolve a website name to an IP address. Or specific email server errors like SMTP error codes.
Wow. Seeing it laid out like that really shows how the model helps categorize and tackle problems.
Absolutely. It turns chaos into structure.
Okay, so it's great for fixing things when they break.
Yeah.
But what about preventing problems, specifically security threats? Does the OSI model help with cybersecurity too?
Immensely. It provides a fantastic framework for understanding where threats can occur and for building layered defenses, what we often call defense in depth.
Defense in depth.
Yeah, the idea that you need multiple layers of security control, so if one layer fails, others might still catch the threat. The OSI model helps security teams classify risks and vulnerabilities according to the specific layer they target.
So you can apply the right defenses at the right layer.
Exactly. Instead of just having one big firewall, you think about security at each stage of the data's journey. For instance, a DDoS attack could target layer 3 by flooding routers, or it could target layer 7 by overwhelming a web application with requests. Knowing the target layer helps choose the right mitigation.
Can you give examples of threats and defenses at different layers?
Sure, let's walk through them. Layer 7, application. Threats here include malware in emails or downloads, SQL injection to attack databases, cross-site scripting, XSS to attack users' browsers, and exploiting software bugs. Defenses, web application firewalls, WAFs, specifically designed to inspect application traffic, regular software patching, and security-aware coding practices. Layer 6, presentation. Often exploited through phishing, tricking users into trusting fake certificates or entering credentials on fake sites. Also, man-in-the-middle attacks trying to decrypt traffic. Defenses include strong encryption, TLS/SSL, with proper certificate validation and, crucially, user education to spot phishing attempts. Layer 5, session. Session hijacking is a major threat here, attackers stealing a user's active session cookie or token to impersonate them. Defenses involve strong authentication, secure and often short-lived session tokens, and multi-factor authentication, MFA. Layer 4, transport. Classic threats are DDoS attacks aimed at exhausting server resources like SYN floods and port scanning where attackers look for open ports to find weaknesses. Defenses include stateful firewalls that track connections, intrusion detection prevention systems, ASAPTES, and specialized DDoS mitigation services. The Layer 3 network. Man-in-the-middle, MID-M, attacks intercepting or modifying traffic between networks. IP spoofing, where attackers fake their source IP. Defenses are network firewalls, filtering based on IP addresses, secure routing protocols, and using IPsec for encrypted and authenticated communication, especially in VPNs. Layer 2, data link, sniffing traffic on local networks, especially unsecured Wi-Fi. MAC spoofing, or ARP spoofing, to impersonate legitimate devices on the LAN. Defenses include using switches instead of hubs, enabling port security on switches, using VLANs for segmentation, and strong Wi-Fi encryption like WPA2 or WPA3. Layer 1, physical. Good old-fashioned wiretapping, physically accessing network equipment, eavesdropping on wireless signals, or signal jamming. Defenses are primarily physical security, locked rooms, secured cables, encrypting signals whenever possible, and maybe even advanced monitoring for signal anomalies.
So thinking in layers helps build a much more comprehensive security posture.
Definitely. It ensures you're considering vulnerabilities and defenses across the entire communication process, not just at one or 2 points.
We've covered the official 7 layers in detail, but anyone who's worked in IT or networking has probably heard jokes about Layer 8.
Ah, yes. The infamous Layer 8, the bane of many an IT professional's existence.
It's not in the official OSI standard, obviously, so what is it?
Layer 8 is the unofficial, often jokingly referenced layer that represents the human element, the user, or sometimes the politics or processes surrounding the technology.
So when something goes wrong, and it's not the cables, not the switch, not the router, not the firewall, not the software.
It's probably Layer 8. You hear it all the time on IT forums. The problem exists between keyboard and chair.
PEBCAC.
KEBCAC. Or sometimes pick the nice problem in chair, not in computer. It refers to human error.
Yeah.
Users clicking malicious links, misconfiguring settings, accidentally deleting things, or just not understanding how something works.
But it's not always just the end user, right?
No, absolutely not. Layer 8 can also encompass organizational issues. Some people call it the political layer, or the financial layer, or the bureaucratic layer. Think about management decisions, like not approving the budget needed to replace failing hardware.
Or company policies that get in the way of security.
Exactly. Or silos between departments that prevent effective communication and troubleshooting. Sometimes the hardest problems aren't technical at all, they're organizational or procedural.
Are there other unofficial layers people joke about? Layer 9, Layer 0.
Oh yeah, the jokes extend. You might hear layers 9, 10, 11 representing increasing levels of management or bureaucracy. And we already touched on layer 0, sometimes referring to the absolute raw physical medium, like the fiber itself, or even, as one witty comment put it, the air between two Wi-Fi antennas.
So while it's humorous, there's a real truth there, that technology doesn't exist in a vacuum.
Precisely. It's a common refrain. It's always layer 8, or it's DNS. It highlights that even with the most perfectly designed technical architecture based on the OSI model, the human and organizational factors, the soft layers, often introduce the most complex and frustrating problems. It's a crucial reminder.
And that really wraps up our deep dive into the OSI model. It's quite a journey. From Sarah's dog photo starting as an idea, becoming data, getting wrapped in layer after layer, sent as raw bits, navigating routers and switches across the globe, being meticulously unwrapped and reassembled.
And finally appearing on Max's screen. It truly is a testament to the structured genius behind our interconnected world.
Yeah, we've seen how this framework, even if it seems abstract, provides this vital common language, a way to understand data flow, to systematically troubleshoot those frustrating network glitches.
And even to build stronger, multi-layered cybersecurity defenses.
It definitely reminds you that every single click, every stream, every online interaction is this incredibly complex, multi-layered ballet happening at blinding speed, mostly invisible, but astonishingly precise.
And if we connect that to the bigger picture, the OSI model, even though it technically lost the protocol wars to the more pragmatic TCP/IP suite, it remains the foundational intellectual blueprint. It's how we think about networks.
The conceptual bedrock.
Exactly. Its principles underpin so much of network engineering, design, security. It's not just for network gurus, it's the invisible scaffolding supporting everything from your video calls to just loading a simple web page. It gives you that critical lens to understand our digital lives.
So maybe the next time you hit send or stream a movie, take a second to consider that intricate, layered journey your data is taking, just beneath the surface.
Yeah.
It really is decades of engineering brilliance at work.
Which I suppose raises a final important question for you to ponder. As our digital world gets even more complex, think about 5G, AI managing network traffic, maybe even quantum networks someday, the explosion of IoT devices. How might these foundational layered models like OSI need to evolve? Or perhaps will they need to fundamentally break to accommodate the sheer scale and speed of future data transmission? And what new layers, official or unofficial, might emerge in that future?